Hello, wonderful people. Welcome to Cosmology Talks. Today we have Sankarshana Srinivasan, who's a Humboldt Research Fellow at LMU in Munich. Shankar is talking today about constraining or detecting modified gravity using large-scale structure data in as model-independent a way as possible. This is difficult because much of the information from large-scale structure is on nonlinear, or at least quasi-linear scales, so one can't just use perturbation theory. And this is also precisely where baryons are kicking up a fuss and ruining the cleanness of measurements. So there's a problem even for lambda CDM and other deviations from lambda CDM, but it's especially hard for modified gravity. It's simply impossible to run a new hydrodynamical simulation for every possible modification of gravity. But Shankar and collaborators have made some headway into this, and have shown that with a clever way to make the cut on what distance scales one includes in the analysis, one can still get much of the nonlinear information without needing to worry about baryonic effects so much. If gravity isn't general relativity on cosmological scales, we'll need work like this to find out. So welcome, Shankar. Do you want to start by telling us briefly about your paper?
So the paper is about how we can optimally test gravity using stage 4 large-scale structure surveys. And the reason I think, and a few other people on this planet think that this is a good idea is because, of course, in cosmology, we already have a bunch of these things that we can model really well. We have this lambda CDM model that works really, really well. We can predict things really accurately and precisely, but we don't have a fundamental explanation for what dark matter is, which is the CDM. We don't have a good explanation for why the universe is accelerating and expanding, which is linked to lambda or the cosmological constant. This could be because we just don't understand gravity well enough, and there may be some inconsistencies with the way we model it, and that is what causing these things to appear as artifacts. So this is the motivation for modified gravity, and the kind of elephant in the room with modified gravity is that it's really hard to model it on nonlinear scales, and these scales are going to dominate the data that surveys like Euclid, LSST, Sphere X, and so on are going to produce. So the paper is a Fisher forecast that takes a formalism that Dan Thomas developed, which was covered in the previous cosmology talks about this topic, and propagates it through simulations of n-body simulations of modified gravity. And those papers, which were precursors to this paper, basically allowed us to predict the nonlinear matter power spectrum as a function of these parameters mu and eta that basically scale up and down the Poisson equation or the lensing potential up or down. And we bin these parameters in redshift, and then we say, okay, give me a survey, give me a redshift binning, and I can tell you what the power spectrum is, and therefore try and constrain these parameters in a model-independent way using nonlinear scales. So this is what the paper has now shown that you can do. You can go from first principles to some binning scheme to constraints on cosmological parameters plus modified gravity parameters.
What were the new insights that you obtained through doing this, and why are they important?
Of course, the kind of obvious thing is that the more nonlinear information you include, the better your constraining power. Key insight. But this is something that everybody knows. But then the problem with nonlinear scales is that you can start pushing, but then eventually you're kind of swamped by baryonic feedback, which is this uncertainty that comes from the fact that we don't know what the astrophysics is doing to the power spectrum on nonlinear scales, on small scales. So one of the key insights we showed is that you can mitigate for this using this thing called the BNT transform. Yeah, so what I've done here, so mu and eta are the modified gravity parameters, right? Ignore the subscript 1, that's just telling you that it's one specific redshift bin. But what I've done here is I'm pretending that there's two people. One person pretends that they know exactly what the baryons are doing, and so they fix the baryonic parameters to the fiducial value, which for some reason they believe is the correct value, right? And that's how I produced these blue contours. Right? You
And this is
vary.
in some model of baryonic feedback.
Yeah, exactly. This is this HM code one parameter model of baryonic feedback, where TAGN controls the strength of the feedback. And so this is how I produce the blue contours. And the red contours, I do what every cosmologist should do or does, where I marginalize over the baryonic feedback parameters, right? And of course, it seems like as though the modified gravity parameters are kind of affected less than omega matter, right? As you see in this plot, but this could easily be just because of the fact that we choose to model for this paper the baryonic feedback with just a single parameter model, right? In principle, there could be a lot more freedom, and then you could also have the problem could be equally bad for mu and eta.
I presume you will go into this eventually, but in just one sentence, can you just give people a physical intuition of what mu and eta are?
Mu is a dimensionless rescaling of Newton's gravitational constant. Right? So in GR, Newton's gravitational constant is what it is, and in modified gravity, it's promoted to a function of space and time. And in this case, we just treat it as a parameter that's binned in redshift. Eta is similar, but it basically rescales the lensing potential. So it basically scales up or down the equation that enters into your lensing CL computation. Right. So you can see basically that because I did this, you can effectively quantify how much the baryons are affecting your constraints, right? So instead of doing this, what you could do is apply this thing called this BNT transform, which basically is a linear transformation of the lensing kernel. And what it does is, because it's a linear transformation, it preserves the information, but it kind of reduces the overlap between the lensing kernels and doesn't make them so super wide. So you can apply your scale cuts based on the matter power spectrum, based on your knowledge of the matter power spectrum. Right? So there becomes a clearer definition of what K and L, how they are related. So here what I've done is I've applied the BNT transform. And what this allows you to do is this allows you to apply a scale cut that is controlled by basically the K or the scale up to which you trust the matter power spectrum, right? So basically what I did was I knew that baryonic feedback essentially starts to matter at K, starts to matter a lot, or at least for this single parameter model, it starts to matter a lot at K larger than 0.5 megaparsec inverse over H, right? And so I applied the scale cut based on this value of K, and then repeated this process of fixing and marginalizing over the baryonic parameters, and you can see that I get agreement regardless of whether I do this. Right? So essentially, for this way of applying your scale cut, you can push to K of 0.5 or 0.4 or whatever you believe is reasonable without being swamped completely by baryons. And I think this is a very, very cool result.
I guess I'll save this for discussion later on, but you've shown this in the HM model of baryonic feedback, I guess. Whether that model is reflective of what all of these stage 4 surveys are going to actually see in the world, I guess, is slightly different. Maybe there it's more complicated, but we can discuss that later.
So I mean, it's almost sure that the baryonic feedback is more complicated than HM code. This sort of what we've done here, but I think what definitely holds is, irrespective of how complicated or how much freedom there is in the shape of the matter power spectrum, because we don't know what the baryons are doing. I think most sort of hydrodynamic simulations kind of agree as to where it starts to matter as a function of the scale. So my kind of elevator pitch for using this is that even if you don't believe that your baryon model is right in terms of how much freedom there is in the power spectrum. So long as you're aware of the scale at which it starts to matter, you can safely model up to that scale, right? Whereas with regular weak lensing, you have, because the lensing kernel is so wide, you have you never really have control over what scales enter into your CLs.
I see. Okay, yeah, I'm looking forward to seeing how the transformation works then in the rest of the talk. Cool. Yep.
So the last thing I wanted to say, in terms of like results that kind of surprised me a little bit, was that, so one of the open questions when you do this kind of binning in the modified gravity, excuse me, in the modified gravity parameters, is how many bins can you reasonably constrain with some survey, right? And this we looked at by varying the number of bins in our Fisher forecast. And I kind of expected that the fewer bins there are, the better the constraints will be, just because you would expect that, naively, right? The fewer parameters you are, so long as these parameters are, completely, as long as these parameters aren't completely uh, useless for your data, you would expect that fewer parameters means better constraints. But this is not what we saw. We seem to see that there's some sort of sweet spot in terms of how many bins you want uh, in your modified gravity, redshift bins you want in your modified gravity parameters. And I think this is because of the size of the bin and the scale cut we're employing. Because the longer the bin gets, the stronger the signal gets, but also I think the more degeneracies you start to see. It's very hard to sort of qualitatively describe, and it's not something that I totally understand myself right now. But we seem to see that there's some kind of sweet spot.
Awesome. Yeah, let's get deeper into the background now about why this is valuable and what the problems were you were trying to solve.
Right. So let me go jump straight into it. Right. So of course, we know, as I said earlier, we know that dark matter and dark energy are sort of key ingredients in the lambda CDM model that has become extremely successful in cosmology over the past decade. But we don't know what they really are, and hopefully modified gravity might be something that could perhaps explain one or two, both of these things. But the other big motivation, and for me, actually, this kind of matters a bit more, strangely enough, because it's just not talked about much in the literature. But so GR, while it's of course been extremely successful, is one of the best tested models, theories that we have, right, in physics. And of course, it's very beautiful, and everybody loves GR. But having said that, there is a regime where GR has really not been really well tested. However, we assume its validity over that regime whenever we say that lambda CDM is an accurate description of our universe, right? And what I mean by that is, on very, very small scales, right? Where, so solar system scales, so think of like light deflection in a solar eclipse, or perihelion precession, or neutron stars or black holes colliding, and so on. These are very, very small scales when it comes to cosmology, right? They don't really enter into any cosmological analysis. But this is a one sort of strong field, very, very nonlinear regime where GR is very, very well tested, right? So that's sort of on the left on all these, on this plot. On the right, sort of linear scales, is where cosmological perturbation theory is valid. So the density contrast is small, and you can do cosmology really, really well, right? So this is where all the CMB constraints and current large-scale structure constraints also live, right? But there's an entire range of scales in the middle where we kind of assume the GR works, and yeah, we kind of assume the validity of GR over this nonlinear regime every time we say that lambda CDM is true. And as good scientists, we should be testing, we should be doing null tests of GR to be absolutely sure that there's nothing sort of strange or inconsistent that's happening on these scales, right? And maybe this is just me being a bit provocative here, but there's already some hints, sigma 8 tension, this tension, that tension, that maybe there is something going on these small scales that we don't really understand.
It could be that dark matter, dark energy is a cosmological constant, and gravity doesn't act how we expect it to on nonlinear scales.
Yeah, and it would be, it would be exciting if that was the case, right? Irrespective of this dark matter, dark energy problems. Okay, so modified gravity was kind of invented because of dark matter and dark energy historically, and the way that people kind of did modified gravity traditionally is to invoke this thing called Lovelock's theorem, and this gets a bit technical here, but basically this modifies GR, either couples GR to extra fields, either it adds more dimensions, or it violates the weak equivalence principle, or it violates this thing called diffeomorphism invariance, which is basically telling you that GR is a consistent metric theory of gravity. So this might involve non-locality of some kind. So basically, this is what traditionally how people did GR. They modified this Einstein-Hilbert-Lagrangian, and because there's so many things that you can do, there's a whole sort of zoo of modified gravity models, right? And some of these people have already seen, like so F of R, Hondesky, and so on. These might be kind of familiar names to people. However, so again, on linear scales, linear perturbation theory, you can kind of try and parameterize these, or at least a big subspace of this model space that I'm looking at here, really well, because you can capture all of the phenomenology that comes from this into a few sort of free parameters, and you vary them, and then you run MCMC, and then you can fit for them, right? This is what Planck did, and Des and a few other large-scale structure surveys, kids as well. This is how they basically did the linear constraints on modified gravity, right? But however, once you go to nonlinear scales, you end up having to predict the nonlinear matter power spectrum model by model by model, right? And this is just, of course, n-body simulations are extremely computationally intensive, expensive, and so it's really not reasonable to do this, given already how much demand there is for computational resources today. Right?
Even just within modeling lambda CDM.
Exactly, right? And this again ties back to sort of baryons and so on. There's lots of reasons to run simulations, and this is something that is going to be a limiting factor going forward, whether we like it or not, right? So this kind of motivates a method to try and parameterize modified gravity consistently in the nonlinear regime, right? And this is what Dan Thomas's paper way back in 2020, which you covered in Cosmology Talks, does, where you basically end up with these two equations by expanding the FRW metric in a 1 over c squared kind of expansion. So this is most similar to like a post-parameterized Newtonian expansion, but this is now applied to cosmology, and so it becomes a post-Friedman thing, right? And in this case, what you end up with is these two free functions, mu and eta, right? And in GR, mu and eta are generic functions of time and space. And our approach, so of course what you could do is say, oh, if I give you a model, you can predict what this mu does as a function of time and scale, right? And this is always something you could do. But again, this leads you back to the previous problem of having to do this model by model, and this takes a lot of computational resources. So what we do is we decide to say we don't really care about what the predictions for mu are. We just want to bin them for and eta are. We just want to bin them in Redshift and eventually in scale. As of now, we've just stuck to Redshift because, as you will see, that's already pretty complicated enough. But eventually, we want to move to time and scale bins. But the point is, we want to try and ask the question: if we have mu not equal to 1 in some Redshift bin, will I be able to pick it up with Euclid or with LSST and so on? So basically, this formalism is a really good, or designed to be a good null test for GR, right? Because if I let's say divide mu into a bunch of Redshift bins and then do the analysis and find that mu is 1 everywhere, this is a good way to kind of rule out modified gravity, irrespective of what the prediction might be, right?
Yeah, or at least constrain it to be no bigger than a certain amount.
Yes, exactly, right? So this is kind of like a model independent or model agnostic framework, if you will.
I guess it's not 100% model agnostic because, as you say, quasi-static limit, weak field, low velocity regime. So if you go back, I mean, you don't have to go back literally, but if you go back mentally to this kind of flowchart you had, is that quasi-static limit basically covering everything on that flowchart, or are there some holes that this limit is not covering?
So there are definitely some holes. So the only models in modified gravity that even have nonlinear predictions are f of r and DGP, right? I would say that, so formally in this language, so long as the vector perturbations in the universe remain small, so in any model where vector perturbations aren't somehow growing, this model is valid, right? So basically, any model with a reasonably well-defined Newtonian limit, right? This model is valid, or this parameterization is valid, right? And in some sense, this kind of, you'd hope that this kind of covers most of the important models, because we know that the Newtonian approximation is extremely valid in our universe, because we use n-body simulations to measure the power spectrum on nonlinear scales, routinely in lambda CDM, right? So so at least for the model space that we care about, or we think reasonably describes our universe, I think that this formalism is valid.
I guess some people might want to push back against the weak field part there. I guess that it could be that the limit that approaches Newtonian physics is not kind of simply connected in any simple parameter space to the limit that is the FRW metric, and that the metric perturbations of an FRW metric trying to describe our universe would be very, very large. I'm thinking about people who are interested in the concept of cosmological back reaction, where perhaps so I guess this isn't covering that perhaps either, but one can't cover absolutely everything.
Yeah, this doesn't cover. Yeah, you're absolutely right. Yeah, so this covers. So for this formalism, delta need not be small, but of course phi and psi do, right? Or we assume that they do anyway. So yes, you're absolutely right that cosmological back reaction isn't covered by this. But well, cosmological back reaction is something I'm very interested in as well. So
a different approach to what you're doing might be this kind, which is this other approach I'm about to mention is super popular throughout fundamental physics at the moment, but the effective field theory approach, where you would say we go beyond GR and require certain symmetries to still be satisfied. Let's write down what it could look like. And I guess you could kind of do both at the same time. And what that would mean was just you'd be putting some restrictions on the form of mu of AK and eta of AK by imposing some sort of symmetry. So I guess you're slightly more general than that. But that's like, it's not quite model independent, because it's like model class, and like you restrict yourself to a class of models, perhaps. Maybe not just F of R, but something a bit more general than that, and then.
yeah, you're right. Yeah, so yeah, EFT of LSS is, of course, and you're bang on, right? This language would basically assume some kind of functional form for mu and eta. And people have actually done this for modified gravity. There are a few papers floating around where people have applied the EFT of LSS to modified gravity. Maybe not exactly in this mu eta language, but this does exist. People have done this. And yeah, so I would say that so something like this would be a good thing to do to kind of see if there's any inconsistencies in the data. If there are, I wouldn't really use this language to work out what the underlying model is that's producing those inconsistencies, right? Let's say we had a detection of mu not equal to 1 in some redshift bin, right? I wouldn't really pay too much attention to the precise details, so long as I was absolutely sure that mu isn't 1 in that bin. What I would then do is do something more sort of theoretically principled, like EFT LSS or something similar, to then work out exactly what the model is that.
I suppose it would still be like a lamp post saying, hey, it's this scale and this redshift that you should care about. But
Yes, exactly. Yeah, that is what it's designed to do, right? It's designed to kind of say, oh, there's some inconsistency and it seems to be coming from here. Right. So our sort of initial simulation. So what we do is, so mu only affects the geodesics of massive particles, right? So to kind of probe the matter power spectrum and modify gravity, the only thing we need to worry about is mu. So what we did was we implemented this first sort of modified Poisson equation, the top equation on the screen, into an n-body simulation where we had a functional form for mu that looked like this, a kind of step function, right? So mu freely varies in some redshift bin, smoothly goes to some value and then comes back, right? And this sort of step function was then shifted around in redshift, and its width was also varied in different bins, right? And this is what we did way back in 2021, right? And what we did was, so at that time, I was just sort of starting out in Euclid. And in Euclid, people were considering using HaloFit to measure the power spectrum for modified gravity on nonlinear scales, right? And HaloFit does this prediction by taking the input linear power spectrum, right, and spitting out a nonlinear prediction, right? So what we did in our first paper, which was just kind of like a precursor, is we basically set up our simulations, the mu in our simulations, in such a way that all the redshift bins have an identical linear matter power spectrum at redshift 0, right? So the redshift bins all have equal incremental growth in them, so that at z equals 0, you would have an identical kind of sigma h parameter in all these simulations, right? So we divide our simulations into mu sort of stronger gravity, so mu larger than 1, and weaker gravity in mu less than 1. And in all of these redshift bins that I've shown here, basically they all have the identical, all these simulations have an identical linear matter power spectrum. Right? And the reason we did this was to kind of test this idea of whether with just a linear input, linear power spectrum, can you even come up with a good prediction for the nonlinear matter power spectrum, right? And I'm kind of foreshadowing the result, which is no, right? Because depending on when you modify mu and for how long in redshift you modify mu, the nonlinear shape of the matter power spectrum can vary a lot. What I'm showing here is the ratio of the power spectrum relative to lambda CDM. And you can see that on linear scale, so small k, all the simulations agree with each other, they kind of sit on top of each other. But as you go from linear to nonlinear scales, you see that they all diverge. And they all have different nonlinear tails. And this is because the nonlinear physics that kind of gets modified depends on what epoch you introduce modified gravity. Okay. This kind of shows that HaloFit doesn't really work because HaloFit doesn't really take into account the modified gravity parameters. It only takes the input power spectrum, right? So, of course, you don't want to run an n-body simulation every time you predict the matter power spectrum or do a prediction for the matter power spectrum. And so what we did was we used this code called React, which predicts this thing called reaction, or the ratio of the power spectrum in modified gravity relative to lambda CDM. But in this case, the lambda CDM power spectrum is rescaled so that the linear power spectrum, so that this reaction is sort of unity on linear scales. So in other words, this is the ratio in modified gravity relative to lambda CDM with a different sigma 8, kind of matches your model of choice. So this is called the pseudo spectrum. It's just a calculational tool because as you can see, the reaction is always unity on linear scales. And using this kind of pseudo spectrum as your linear power spectrum in a halo model allows you to model the transition from linear to nonlinear more accurately, right? And you can kind of see this, right? Like if I plot the ratio relative to lambda CDM as is, you see this kind of quasi-linear behavior at about k of 0.1, and this disappears when I plot the reaction, right? Because this is kind of taken into account by the fact that lambda CDM has been rescaled. So sigma 8 is different, and this kind of captures this quasi-linear physics better. Right? So React is a code that for an input mu and input cosmological parameters spits out a reaction, right? And we showed that this works really well. We showed that React works really, really well to predict the matter power spectrum in our simulations, right? And I should say that React isn't something that I came up with. It's something that Matteo Cataneo, Ben Bowes, and Alex Mead, and so on, a lot of people developed over a long time.
How much is this a consequence of the fact that your mu is scale independent? Like if you had a mu that was only kicking in at those quasi-linear scales, presumably this would no longer be true because that would be where it is most physically relevant.
I think that's a good point. I think React, so scale independence is something that we haven't introduced in our simulations yet, right? But having said that, I think React has also been shown to be able to predict the power spectrum in something like f of r, which does have a scale dependent power spectrum. And this, if you map f of r to this formalism, a scale dependent mu as well, right? So I think it's still doable with scale dependence. But of course, f of r is a very particular scale dependence, right? So in all generality, I don't really know. We'd have to run the sims and redo all of this analysis to check.
And also when you're plotting these values like plotting these curves for particular values of mu, are these values of mu that are deliberately chosen because they're not ruled out by stuff happening on linear scales? Because I presume a big enough mu would cause deviations in the CMB and this and that.
That's right. Yeah. So all of this is allowed in the CMB. But okay, this is slightly old work now, and I think 1.25 is definitely ruled out. But everything else, yeah, is still allowed in.
I guess then what I was imagining, and okay, maybe I'm being contrived, and I just don't feel like I'm being contrived. But anyone outside would be like, Sean, you're making a super contrived argument. But I guess what I was imagining is if you did have a scale dependent mu, then on those quasi-linear scales, it could be a lot bigger than what you're allowed if you have a scale independent mu, because a scale independent mu has to affect the large scales, whereas a scale dependent mu is only affecting the quasi-linear and small scales, so it could be much, much, much bigger. I guess that's kind of what I had in the back of my mind.
That's exactly right, right? And in modified gravity, people do this all the time, right? They have this thing called screening, which which is the opposite argument, right? Where on very, very small scales, we know that gravity is GR, so we have to kind of force mu to go back to 1 on very, very nonlinear scales, right? But of course, this is also true now to some precision, even on linear scales. So yes, in principle, a scale dependent mu, of course, you have a lot more freedom, and in a purely time dependent case, you don't have that. Yeah, but of course, there's also the other thing where now, excuse me, in our simulations we kind of switch on only one bin at a time, right? If you have some kind of really wacky kind of modified gravity model going on in the background, you could have multiple bins where in one bin you kind of make gravity stronger, and another bin you make gravity weaker, and then at z equals 0 you'd kind of measure the same linear power spectrum. But on nonlinear scales you might get something different. So even with time dependent mu, you could still sort of, in a very sort of maybe in a very contrived way, you could still come up with a way to keep your linear physics the same.
Yeah, you did kind of anticipate another question I was going to ask, which is kind of like the constraints in a bin by bin one when you do them independently like that. How independent would they be if they happened at the same time? And I guess that the physics might be independent. I don't know. I mean, tell me whether the physics would be independent, but of course the observations won't be independent because what you're seeing is kind of the integrated effect over all time. But it might even be that the physics isn't independent, that if you have a bigger mu for a little while, structures form and go nonlinear earlier, and then lowering mu might make the linear power spectrum come back to what it previously was, but you can't undo what's been done on the nonlinear scales. So it seems like the bins might not even be independent physically.
Yeah, that's exactly right. Yeah, I fully believe that, and I think all our simulations kind of show that already. Yeah, so I think, yeah, you could evade the linear constraints, but I think if you come up with a consistent way to kind of mitigate for baryons, mitigate for other small scale physics, you definitely pick up that the bins aren't completely independent of each other. Yeah. So what I'm plotting here, by the way, is the kind of first is the smallest k at which the tool that I'm using to predict the matter power spectrum fails to match our simulations, right? At the level of 3%. So a larger bar means sort of accuracy over a larger range of scales, right? And you can see,
Because bigger K is smaller scale. So if you've gone to a bigger K, you've gone to smaller scales. Yep.
yeah, exactly. And this is so this shows that kind of React kind of outdoes halo fake pretty much all the time in our simulation.
I mean, you're even seeing, you're sort of even claiming there that React is doing better than your simulations because you've got the convergence threshold. But I guess you can't test React to better than the dotted line.
No, yeah. I mean, it's just, yeah, it doesn't really. I don't really believe anything that's going on beyond even the blue line, which is where the authors of React have tested it up to, right? So anything beyond that is just, perhaps a happy coincidence, but I don't really want to make any strong comments about that. Yeah. Okay. So what we then did was, so we came up with this way to bin mu in terms of the linear growth factor and the where the bin is, so the midpoint of the bin. So we used that as a way to kind of parameterize our bins, and we came up with a bunch of simulations associated to a specific growth factor. So the color indicates some value of the growth factor, and the position of the points indicates where the bin is, right? And so we kind of validated React formally inside this weird shape that these data points span, right? And why do we choose these values? Because in a few papers where people did Euclid forecasts, this is the size of the bin that they sort of typically care about. Santiago Casas and a few other authors, Martin Kunz, Matteo Martinelli, and so on, did a forecast a long time ago where they considered binned mu, but this was a purely linear scales thing. Yeah.
Okay, good. Can I ask kind of what feels like maybe is a really stupid question here, but there's no physics in this plot, right? This is just telling the redshift range and median redshift where things happened. So it's just kind of telling us where the models existed. Okay. So delta Z is just for how long mu was different for.
Yes, that's right. Yes. Okay, so but what we found, which I thought is pretty cool, is that we found that just using React out of the box kind of doesn't do as well for every single data point on this on this plot on the left, right? But what you can do is you can kind of systematically modify the concentration mass relationship, right, in React as a function of mu, right? And what I did here was to rescale the amplitude of the concentration mass relationship, which is an input thing into the Halo model that React uses. And I found basically the same sort of functional form for this rescaling for all our choices of d of z and z midpoint, right? So this is kind of like a fitting function for the concentration mass relationship that we found sort of empirically from our simulations, but we found that this shape kind of persists, right? And so this is a way to kind of improve the accuracy of React and sort of formally sort of say, okay, over all of these redshift range, over all of these redshift bins that's on the left plot over here, React is accurate to within 1% up to about k of 0.5 and is accurate to within 3% up to about k of 1.
So just for people who maybe have completely unfamiliar with Halo models, when you're saying concentration mass relation, what you mean is when you've got a halo that's out there in the universe, so something that a galaxy or galaxy cluster has fallen into or formed inside of, the concentration, maybe what I'm about to say is even just literally true. It's like a parameter in the NFW model, but perhaps you're going more general than NFW. It's kind of measuring how compact it is. Like it's not measuring its full. Two halos could have the same radius and same mass, but one with a bigger concentration parameter, that mass is kind of more tightly bound in the center and decays away faster compared to less tightly bound and decays away more slowly. That's all correct? So yeah, so the concentration mass relationship is showing that as you get a bigger halo, you do expect the concentration to kind of, as it get more concentrated or less concentrated for a bit?
Less concentrated. So the halo gets kind of more spread out in some sense. Yeah, so that when you modify mu, that this obviously starts to change, right? So the typical size of the halo or the typical sort of scale radius of this parameter that enters into the NFW profile also is sort of systematically affected by when and how you modify mu. Okay, so of course now we're getting to the point of how does this actually affect the cosmological observables we care about in large-scale structure. So this enters into the CLs in this way, right? So we use the standard sort of Limber 2D projection of the power spectrum, which is computed in this way, with the W's being sort of kernels that are different for different probes. So the clustering kernel is unaffected by mu and eta directly, but of course, because mu affects the power spectrum, the clustering CLs are affected by mu via the power spectrum. However, lensing, you can see that mu and eta enter in, right? And so this is how you can kind of constrain eta without having to run additional simulations for it, because you can just model the effect of eta in post-processing of the n-body simulation products. So this is what we do as well. And we find sort of, so I should say now that, so DES does have constraints on mu and eta, right? But as opposed to lambda CDM, where they have these lambda CDM optimized scale cuts, which kind of go a bit deeper into the sort of quasi-linear regime than just a pure linear analysis. For modified gravity, DES kind of were much more conservative, removed literally every nonlinear scale, and so threw away like something like some 75 or 80% of their data, basically. And you can see that in this plot very, very obviously, right? And I'm not trying to knock DES over here, right? I mean, I think that's a very reasonable thing to do, but it just means that that you throw away most of your data, right? And so we found that if you just use vanilla React, you can get up to some scale that's slightly above L of 500, and then if you use kind of this concentration mass relationship fitting function for React, you can get up to L of about just about 1500. So you have much more constraining power, and you can see that I've kind of been a bit provocative here, and I've picked one of our modified gravity models that's very similar to lambda CDM on linear scales, but then starts to deviate on nonlinear scales. But this could easily be true, right? You could have something like this, and then just not see it if you don't have enough constraining power on nonlinear scales. All right, so this kind of brings me into our paper, right? So what do we do? We took React version 2 as well as React version 1, right? So, and then we sort of propagated the power spectrum through a large scale structure pipeline that computes CLs with the Limbo approximation, assuming lambda CDM fiducial values for all of our modified gravity and lambda CDM parameters. And we assumed an LSST year 10 like survey. So there's 10 lens bins and 5 source bins in this. Right. And then we have a bunch of these nuisance parameters. Of course, this is a 3x2, so-called 3x2 point analysis, where you have clustering, you have lensing, and you have the cross correlation, galaxy-galaxy lensing. So you have bias, bin-wise bias, you have linear alignment, intrinsic alignment, as well as baryonic feedback and some photometric redshift estimation errors as our nuisance parameters.
If anyone wants to know more details about these 3x2 point analyses and things, we've had numerous talks by Dark Energy Survey and Kilo Degree Survey who have gone into that in detail. Maybe I'll even have a playlist pop up at the moment. But don't click on that yet. Watch the rest of this talk and click on it later.
Yeah, so in our fiducial analysis, we kind of have 4 redshift bins, but as I told you before, we did vary them, and we found that for some reason our initial choice was the best one. But this wasn't by design. Yeah, it just happened. Yeah. Okay, so again, the key questions were that how much can we push into nonlinear scales without having to worry about baryonic feedback, and is there an efficient binning scheme? Does this change as a function of scale cut? And does it also change as a function of the modified gravity parameters? Okay, so I told you earlier about this thing called the BNT transform. What it does is kind of linearly reweights the lensing kernel to reduce the width of the kernel, and also therefore reduces the overlap between tomographic bins. So what this allows you to do is say that L is sort of consistently related to K via the co-moving distance to the bin that you're looking at. Right. So let me give you a sort of more quantitative understanding of how that looks like. So on the left, I've plotted, and in this case, I've chosen a Euclid-like survey because there's more bins and just kind of the effect is more dramatic in that case, right? So I have 10 lensing bins in Euclid, right? And if I plot the lensing kernel associated with all of those bins, the left plot is what you get, right? And you can see that the lower redshift bins are quite are reasonably narrow, but as you get to higher and higher redshift, you see that the lensing bins get really, really wide, right? And so a value of L sort of mixes up loads and loads of scales, right? So if you wanted to do a scale cut, you don't really have good control over which scales are removed, or indeed which scales enter into your analysis, right? When you apply the BNT transform, these same bins end up looking like the one on as shown on the right hand side. So in the right hand side, you see that the bins are now narrower and there's less overlap between them, right? So you can now say that for any given bin, the average co-moving distance to the bin is chi, right? And then you can say L cut is basically K times chi. And so you can use some K that you believe your matter power spectrum is accurate to inform your scale cut in lensing. And this, I think, is quite powerful.
So the L cut equals K cut times chi is not the BNT transform. The BNT transform comes first, and then it allows you to.
Allows you to do that. Okay, so assuming that the BNT transform is a valid thing that you can do, you can now mitigate for baryonic feedback, because we believe, or we think we believe that we have a reasonable understanding of at what scale it starts to matter, right? So here I've done a K cut of 0.5 H over megaparsec, right? But for shear, I haven't done this L cut and K cut correspondence because I haven't implemented the BNT transform. So what I've done here is I fixed to produce the blue contours, I fixed the baryonic feedback parameter, whereas for the red contours, I've marginalized over it, right? And this kind of quantifies how important baryonic feedback is. And then when you apply the BNT, now you just have a K cut, because the L cut and the K cut has a reasonably well-defined relationship. And now you can see that kind of all the contours agree, irrespective of whether I marginalize or not over the baryonic feedback parameter, right? So this 0.5 number might seem a bit large to some people, but this is because typically when you look at baryonic feedback plots, you see it in physical units. So this H is kind of put back in. So if I put H back in here, then you end up with something like 0.2 or 0.3 or something, right? So this 0.5 is kind of an artifact of the fact that I put H into my house. Right? So I think this is a very cool result, right? Because this is something that people always kind of moan about or worry about in cosmology, even in lambda CDM, irrespective of modified gravity.
People might think K cut is large more just because they've got intuition based on the left hand side, right? Where it is a scale where you do have to worry about baryons because you're getting contributions from angular scales that are smaller and therefore do matter. So, I mean, this is the central thesis of this is what you said was one of the most important results, the fact that you can make a more aggressive K cut because you're doing it more smoothly, I guess, or not smoothly, cleanly.
Yeah, exactly. Yeah. Okay, so now I want to move on to binning strategies, which is basically you want to now understand for a given survey, how many redshift bins do you want for mu, how many redshift bins do you want for eta, do you want them to be equally sized, or do you want them to be parameterized in using this linear growth parameter that we do. And we tested this, right? We divided the redshift range between 0 and 3 into 5 bins. In one case, we equally spaced these bins. We basically decided that delta Z of those bins to all be the same. And in the other case, we did it the way we do, which is with equal linear growth, right? And we found, but the point is that the equal spacing bins are associated to a larger error, because again, the as you go from large a high redshift to low redshift, the width of the bin, if you keep the width of the bin the same, sort of more and more nonlinear physics starts to enter, and so your uncertainty from not small scale physics like intrinsic alignment or baryonic feedback and so on starts to matter more, right? Whereas for equal growth bins, you kind of naturally reduce the size of the bin as you go from high redshift to low redshift, right? And so this kind of puts a lid on how much uncertainty can enter into your analysis. So we kind of find that so linear growth bins are much better to do this kind of analysis than equally sized bins. The other thing we found is we also found really poor constraining power at Z of larger than 2.1. I think this is because at modifying mu at Z larger than 2.1, for the scale cuts that we employed, all the nonlinear physics was at a scale smaller than the scale cut we imposed. So the constraining power is really
So you don't have a redshift dependent scale cut.
no, yeah, we don't have a redshift dependent scale cut. It would be cool to do that, and we kind of have the machinery to be able to do that now. But in this case, we just stuck to three sort of benchmark choices. So k cut of 0.1, which is kind of the linear one, k cut of 0.5, which is the sort of realistic one, k cut of 1, which is like very, very optimistic.
But presumably, as you've just pointed out, at higher redshifts, those things should all move to smaller scales because things have gone less nonlinear.
Yes, exactly. Yeah. So if you were to do this with data consistently, you probably want to vary your k cut as a function of z. Yes, that's probably something you do want to do. Right. So the other thing is we wanted to, as I said before, look at how many bins you can reasonably constrain for LSST year 10, right? And we found kind of non-intuitively that the average constraining power, the average error on the modified gravity parameters is kind of at a sweet spot for n equals 4 bins. And I think that this is to do with degeneracies between parameters associated with the bin size, but I'm not, like, if someone asked me to lay my life down for that, I probably wouldn't. So this is something that we're sort of still slightly confused about, and would probably want to investigate in a more sort of doing MCMCs and sort of being more rigorous about it. Okay, so again, the constraining power kind of comes from the fact that, as you go from, so here I'm plotting the lensing kernel for LSST, right? For LSST year 10. So there's 5 source bins, and this is how they look like, right? And I've also sort of superimposed the modified gravity bins on top of these lensing kernels in black. And so you would expect that kind of about z of 1, which is where, like, a lot of the information kind of comes from in these in LSSD at 10. Around that is where modified gravity is sort of best constrained. And we find that for the vanilla and BNT transform data vector, that's the bin that's kind of the best constrained bin. So the bin that's around z of 1, right? However, when you add this concentration mass fitting function, we find that that fitting function kind of affects the lowest redshift bin, or this mu1, much more than it affects the higher redshift bin, which is what the right-hand plot shows, right? So the right-hand plot shows the ratio of the CLs with the concentration fit switched on relative to the CL with the concentration fit switched off, and you find that the bigger deviation comes in the lowest redshift bin, whereas the highest redshift bin there's barely any effect, right? So once we switch on the lowest redshift bin, you get really good constraints on those bins when you implement the concentration fit. So this is where sort of these constraints that you see on the right now sort of come from, right? So these mu1 and mu2 are sort of our best constrained bin in our sort of benchmark, or the best constrained model, where you have BNT and concentration, all the sort of physics kind of modeled as best as we can when this fit is included. Right? And this is for a sort of like a realistic choice of k-cut, right? 0.5. Yeah, so React is slow, and it definitely does need emulation, and this is something I'm working on right now, right? And I'm also working on trying to construct this emulator while also validating React for scale-dependent bins or multiple bins switched on at the same time, right?
When you say needs emulation, so React is not it doesn't do the simulations itself. So even then, it's still too slow. What is it spending most of its time doing? Just integrals, or?
Yeah. It's doing an integral over the mass function for the one halo term, so sort of small scales, and this is slow, and it does this, and you have to do this over and over again for every redshift.
So is it, when you say needs emulation here, do you mean of the React model, or could you actually just do emulation of the simulations?
Of React. Yeah, you could do an emulator for the simulations, but that would be much, much more expensive computationally because you need to run lots and lots of simulations.
I suppose also, especially if the bins aren't independent, like having multiple bins is not the same as having what you would get with one bin added to what you would get with the other bin. Then I guess you've got I guess what, it's not a separable problem, that the function. So
Precisely, yeah. And this is why we stuck to the one bin at a time case at the moment, because otherwise you'd need to run like a gajillion simulations before you could even say anything. But yeah, so React is I mean, if you care about 10 models, you could run React as it is, right? But of course we care about a lot more, right? And we have to consistently vary all the cosmological parameters and so on. And React's definitely slower than your average Boltzmann code, and even Boltzmann codes are emulated these days, so React definitely needs emulation. The other thing is, instead of running n-body simulations, I've it's been shown that Lagrangian perturbation theory simulations, so-called COLA, are also reasonably accurate over the scales that we care about. So up to about k of 0.7, 0.8, COLA kind of agrees with Gadget and other n-body kind of codes for the power spectrum. So maybe we could use COLA, which is faster, as a validation tool instead of full n-body simulation. This is also something I'm looking at.
So the heuristic explanation of what COLA and Lagrangian perturbation theory simulator is that kind of you still kind of have n-body particles, but they're given like their initial momentum and then kind of tracked, maybe with a little bit of modification, but not a lot, depending on whether it's second order Lagrangian or not. And that's better than just pure perturbation theory, because you kind of get the overdensities a little bit better, because they can travel quite large distances, which wouldn't be modeled by pure linear perturbation theory, but you don't have to calculate a force every single time step to some degree of accuracy. Cool.
Yeah, exactly. Yeah, very, very well put. Actually, this is exactly why people have found it to be reasonable. And finally, the last thing is, we have all these simulations, and it's probably smart to also try and look at other observables from these simulations. Not just the 3x2 point signal, but also the cluster density profile, voids, the splashback radius of the clusters, the number counts of the clusters, and the number counts of the voids, and so on. These are all things that could potentially be looked at, just haven't been yet.
I had one other question that's maybe interesting, but maybe not. But like in all of your constraint plots, there seem to be a super tight degeneracy between mu and eta, especially in the same bin, but sometimes not even in the same bin. I mean, I think I saw that when you were showing the plots right at the beginning, and I think it's kind of obvious when you show the equation that described the physics of eta, where you had like mu 1 plus eta. Like it's clear that if you increase one, this one, it's pretty clear why mu and eta have this very tight degeneracy. Is that something we're kind of stuck with, that they're always going to be this degenerate with each other, or is there a way to kind of tease out somehow, if we do detect something interesting in mu, that it is mu or it is eta, or what?
Yeah, I think there is something you can do. It's just that with what I have with me, in the sense that with the CLs, there's only so much you can do. But I think, so for something like a spectroscopic survey, for example, where you do like a full shape analysis of the power spectrum, I think you could then kind of tease out just by looking at the shape of the power spectrum and then cross-correlating it with the CL, you could tease out this degeneracy, right? But otherwise, I think it would be really hard to do it. And that's just because of the fact that, again, we're binning mu, and these bins are fairly narrow in redshift. So technically, So you have a situation that looks like this, right? Where on linear scales they kind of agree. I mean, they're kind of on top of each other for mu and eta varying in the same bin, right? Because of this equation, as you astutely pointed out. But as you go from linear to nonlinear scales, because mu affects the power spectrum, while eta does not, they start to diverge from each other, very similar to how you see in this plot. But the problem is that for our binning, uh, this kind of deviation from each other is like a at the level of a few percent. Yeah. So it's this degeneracy, right? So for the lower bins, it's worse, right? Because for the lower bins, you only have cosmic shear kind of contributing, right? But as you go to the higher bins, it kind of gets a bit better.
So yeah, I have one last question that I think is a kind of provocative question, but not provocative to you. It's provocative to the rest of the community. I think, let's say the S8 tension, that was one of the things you said as a motivation for looking at modified gravity. I think if you were to do a poll of the cosmology community and allowed them two options, baryonic physics or modified gravity, the vast majority would say it's some sort of baryonic feedback type thing, or incorrect modeling of lambda CDM nonlinear stuff. Um, how worried are you that the community is just going to iterate and iterate and iterate on different ways of doing the nonlinear physics and different ways of doing baryonic physics until they find something that fits the data? And that if the real universe actually had modified gravity, they've just undetected it by settling on the wrong baryonic physics model. Is there let's pretend for now that modified gravity is the actual cause of the S8 tension. Is there a way of avoiding that horror scenario where for the next 100 years we think baryonic feedback works in some way that we've converged on, and it actually works completely differently, and we could have detected modified gravity in 2026? Is that a horror scenario, or is it avoidable by some like probe of baryonic physics to like properly tease it out?
Yeah. So fantastic question, right? And if you asked me this, like, I don't know, maybe 2 or 3 years back, I would have absolutely said, yes, this is something I'm terrified about, right? But I think recently there are people that worry about this as well, not that aren't just modified gravity people, right? So there's a series of papers by George Eustathiou and Alex Amon, where they do this thing where called they introduce this thing called AMOD, which basically is there's a similar kind of thing. While it doesn't come from any theoretical formalism like ours, it's basically some kind of phenomenological thing that they've invented that suppresses the power spectrum on small scales, right? And what they did was to try and investigate um, whether you would detect a suppression of the power spectrum, so in K space with weak lensing, um, observables over and above baryonic feedback, right? And I think they've shown that it is possible to see this. That sort of you could, with the DES data, you there is some support for suppression of the power spectrum beyond even all of the freedom that comes from the different hydrodynamic simulations. So people are worrying about this. I think it's still something that we should definitely be absolutely wary about. Sort of this kind of how should I put it? This bias towards lambda CDM that seems to have sort of creeped in somehow over the years. But I think this is something now that the community is taking seriously, right? Just because even with this bias, if I asked, I think again, if I conducted a poll as to whether you're satisfied with lambda CDM as a physical model, I think most cosmologists would say no.
Sure. I think cosmologists are kind of like the kidnap victim Stockholm syndrome kind of thing, that lambda CDM has won so many times when cosmologists have thought finally we found a chink in the armor, and then eventually something has been worked out that okay, that was what was going wrong, but like eventually one of these chinks will actually be an actual chink in the armor and not an illusion of a chink in the armor. And I'm worried that we'll, as a community, like because you said that Alex and George's paper, they might also have had a PhD student that they were involved with, but that they Callum, yeah, that they showed that no hydrodynamical simulation effect could mimic blah blah blah, but that maybe is lacking. Like, cosmologists have a lot of imagination, right? And the hydrodynamical simulators might be like, oh, well, there was this parameter that we didn't normally include because we thought it probably wasn't relevant. But if you turned it on, it would actually mimic that. And then the rest of the community would go, oh, well, that's the explanation. We didn't have that parameter turned on. No problem. S8 resolved. Moving on.
Yeah. So this is definitely a big problem, right? So the fact that these hydrodynamic simulations don't converge, I think this is a big issue, right? But so there was recently this paper by Leah Bigwood and Alex Amon is her PhD supervisor at Cambridge. Well, she's at Princeton, but Leah is at Cambridge. And she has shown that you can use kinetics on your Zeldovich observations to kind of model or independently model these baryonic feedback models.
Or measure them, I guess. Yeah.
Exactly, right?
That feels like the hope to me, that find a way of independently measuring the baryons, and then you'd find that this hydrodynamical simulation effect that got turned on actually doesn't work for that, and then you hope that.
Yeah, exactly. Right.
Meanwhile, you and Daniel are shouting in the background saying it's modified gravity, damn it.
So I mean, it'll hopefully all resolve itself eventually, with all of these people kind of putting their heads on their thinking caps on and trying to resolve this. But I mean, I agree that it's definitely the elephant in the room right now, right?
I mean, this is also, of course, why people blind their data before releasing the results. But the problem is you just can't stay blinded forever. Once you've unblinded, someone's going to go, ooh, maybe we should tweak the baryon model.
There's always someone going ooh after you're unblind. I think this is something that you just have to accept, right? It's just a fact of life. Yeah, we'll see how it all works out in the wash. But I mean, it's all exciting. Let's see what comes out. I'm sort of cautiously optimistic, as I say, with large scale structure. I think if anything happens, it should be over the next decade or two.
Awesome. Yeah. So what work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the community?
Right. So I think there's some work that is led by people at Heidelberg, I think, Björn Malte and so on, where they look at tension metrics in a parameterization invariant language, this thing called information geometry, where you kind of come up with a way to look at tensions in your data using this thing called the Kohlberg-Leibler divergence, and use that to quantify tensions, but for different parameterizations. So sigma 8, sigma 12, blah blah blah. I don't know, intrinsic alignment model 1 and intrinsic alignment model 2, right? So smoothly sort of compute the tension for different parameterizations. I think this is something that's super, super interesting and is also something that was going to be extremely relevant, right? Because so there was a paper by Garcia and company. I think David Alonso is on this as well, where they do a nonlinear analysis of year 3 cosmic shear, where they try and combine kids, HSC, and DES, and include a lot of the nonlinear scales. And unfortunately, they find that their constraints show up as a big tension in omega matter. And they claim that they can kind of transport this tension by doing some kind of PCA analysis into a Hubble tension. But the point is, this word tension now is going to be prevalent in cosmology a lot, because we're in that regime now where like a few percent starts to matter, right? So I think this work is really, really interesting and deserves a lot of shout outs.
thanks everyone for watching. If you like this, do subscribe and click the bell to be notified of new videos, and click a like to help with YouTube algorithms, both for yourself and for the channel, because YouTube will know to recommend more stuff like this to you. Oh yeah, and share the channel with your colleagues. If you have any questions or suggestions, leave a comment. Otherwise, check out the talk by Dan Thomas, which was on kind of the earlier steps of this journey that Shankar and Dan are now taking. And thanks, Shankar, for the great talk.
Thank you very much for having me.